So back again, we now consider differentiation proper. Now you realize that in the previous video we recognized the limit perspective of differentiation, right? Where we also saw the use of the first principle. Now anytime you use this formula and you approach h to 0, right, what you have done is differentiation, right? So specifically for this formula, when h approaches 0, what you have done is specifically differentiation, right? And why do we do all of this? Well, the concept of differentiation is actually trying to find a very small change, right? A very small change such that we can use it to approximate things, right? So, for example, say you had a function, right, this way, and let's say you wanted to find the area under this graph, right? Now, before the evolution of geometry to be able to identify the area under a triangle-like shape, right? This is like a triangle-like shape, right? What one way you could have done it is that you could have cut it into very small sections, right? So very small sections called some d of x, right? And now you see that the smaller you cut these sections, the more this part approaches a rectangle, and a rectangle is what length and breadth, right? Yes, so you can just sum this area over that region and you get the whole area under the region. Now that was the use of differentiation. We would see more explicit or elaborate examples of that, but that's what I wanted you to see. Now you also have differentials for various functions, right? And there are several ways. One of them is the first principles, right? So from the first principle, if you have, for example, f of x is equal to x, and you're asked to use the first principle to find it, I hope you remember this formula. You substitute your x, you let h approach 0, and at the end of the day, you find it. You can do the same thing for x squared. If the function is x squared, you get the same thing again. I will not be thorough with this because we had treated it in the previous video. Now, what I really want us to undertake would be for trigonometric functions, right? So let's assume you have f of x equals to sine of x, right? Now, when you try to use the same formula we did as previously, come and end up with this sine of x plus h minus sine of x all over h. Now, if you remember your trigonometry form is multiple angles, you realize that when you have sine of A and sine of B, it's equivalent to what? 2 times cosine of what? A plus B over 2. And you can and that multiplies sine of A minus B over 2. Yes, if you do remember your multiple angles from SHS, that's how it works, right? So if you have sine of A minus B, just twice the cosine of the summation of the angles over 2 times the sine of the difference of the angles over 2, right? So that's what has been applied here. So from here, we can apply that formula on this one to get this, right? And that's what you see, right? So here our A will be what? The x plus h, and our B will be what? The x, right? Yes, and that's what you apply. Now, after you apply it, you realize that you come and get sine of what? You come and get 2 multiplying cosine of 2x plus h over 2 multiplying sine of h over 2. Then you go ahead to simplify. Now in simplification, use the limit theorem. These two are multiplying. This one is multiplying this one as well. Okay, so these two are multiplying, so you can find the limit of them separately. Now when you try to find the limit of cosine of h as cosine of x plus h over 2 as h approaches 0, you'll be left with what? Cosine of x. Why? Because if you put 0, you get what? Cos of x plus 0 over 2, right? Now when you try to find this one, you realize that here it's a bit peculiar, right? Because the limit you inherited was what? Sine of h over 2 all over what? H, right? And you had a 2 here. And remember, in the original expression, you had a 2 at the edge multiplying, right? These two. Yes, you are going to use it. So these two, you can put it at the denominator here. You get it? Instead of these two being the numerator by the sign, you can put it at the denominator, right? Yes. Because I mean, 1 over 1 over 2 is the same as 2, right? So 1 over 2 is the same as 2, right? Now, do you also remember that the identity I asked you to keep in your head, sine x over x is equal to what? Is equal to 1, right? So sine x over x is equal to 1. Yes, now sine x here will represent h over 2. H over 2. You understand? So this will be given 1, right? So at the end of the day, you get 1, and that's the one you see here. Okay, now that will give you the result of what? Cosine of x, right? So what it means is that when you differentiate sine x, you get what? Cos x. It's as simple as that. Now, you see, now you are taking through the first principles to show you where we got the derivatives from. When we get to more complex doings, you realize that we'll be just mentioning them and doing them. But just know that this is where they are from. So we can also try for cosine, right? So let's just do for cosine and probably bring this video to an end. So cosine is also as simple as that. You just go through the same steps. So you are finding the derivative of cosine, right? And you put it in the limit formula. But this time, remember, the limit approaches 0, right? When you're doing derivative, remember the limit approaches 0. So you are trying to find a very small change, right? That's the whole point of the differentiation. So you will substitute it and you get this one. Cos of what? X plus h minus cos of x all over h. Now, you come back to another trigonometric formula, right? Yes, where you have cos of a minus cos of b is equal to cos of a plus b over m is equal to minus 2 sine of a plus b over 2 times sine of a minus b over 2, right? If you'd remember, I don't think that one was shown here. Yes, but that's also one of the special angle formulas. Yeah, so you apply it on this one, right? And you come and arrive at this. Then you continue through the same procedure. So you come and get this h over 2 again. Then you realize the answer is what? Minus sine x, right? The proof is not really hard once you know your multiple angles for sine and your multiple angles for cosine. So you can just try and find on the internet cos of A minus cos of B. Search for this in terms of sine, and search for sine of A minus sine of B, also in terms of what? Cosine, right? That is how you do the substitution, and it's not hard. You just have to know those two. Now you realize that at the end of the day, we get minus what? Sine of x. Now you can go through the itinerary and see it's the same procedure. But what you realize is that when we differentiate cosine, we get minus of sine, right? When we differentiate sine, we get cosine. And we differentiate cosine, we get minus of sine. Now, these are two important differentials I want you to keep in your head, right? We can't go through this whole procedure every time you have a very complex differential, right? So you have to learn these as of now. As we progress, then we will just be substituting because we already know it from memory, okay? Now, there's also another special type of functions which I want you to consider. That is the function which are in the form y is equal to a raised to the power x, where a is a constant. So the example can be y is equal to 2 raised to the power x, right? Exactly. Now, when you're asked to differentiate something like this, how would you do it? Well, you just start by putting it in the same old formula, f of x plus h minus f of x all over h, if you remember that. Then you have to substitute uh, yes, you have to substitute the corresponding variables, right? So you realize that as you allow, before you allow h to approach 0, you realize that a raised to the power x is here and a raised to the power x is here. Remember your indices. A raised to the power x plus h the same as a raised to the power x times a raised to the power h, right? And if I substitute this one for that expression, then it means I can factorize a raised to the power x out, which you see here. Okay, so that's that. Now you realize that the logic is that, see, we come to get a function inside, a function in terms of h inside. and we come to get the a raised to the power x outside, right? So we can just now conceptualize that anytime you have a function raised to the any constant raised to the power x, then our result will be what? A constant multiplying what? A raised to the power x. Now this constant is the limit as the function which was inside what approaches zero, right? Now you go ahead and realize that this would be a constant. This what is here will be one big constant, right? And you have to uh, take care of that. There are other alternative approach. You can even be taking logarithm of both sides and do it, right? But for now, I just want you to see how the whole concept plays out anytime you try to use the first principles of differentiation. So another one is here, and this actually follows from the previous one, okay? It follows from the previous one. So we are trying to find that constant key because we realize that we can't just use the limit theorem to approximate it. If you put 0, 0 here, you realize that this approaches infinity and we don't want that. So first, we try to take logarithm of both sides, and I hope you remember your logarithms. So when we take logarithm of y, we just get log of y, right? When we take log of a raised to the power x, what do we get? We get x log of what? A. Now, then we go ahead trying to do our differentiation. So there are two very special properties in logarithms that I have to show you. Okay, now we'll take this again, but for starters, you have to know when you take log of any number or any expression and the base is e, this is called a natural logarithm, and you can write it as what? Ln of x. Now, that's one property that you should know, okay? And that's one property which we are going to use in their differentiation. And for any general logarithm, this is the formula used in its differentiation, right? If you are giving logarithm to the base any constant, right? It can be b, it can be a, c, right? But if the constant is specifically e, right? E is a special meaning in math, right? Then the differentiation is just 1 all over the function you have here. In this case, we have x, so x ln of the base. The base here is b, right? And now it is that same procedure which we can use to differentiate the logarithmic function on the other slide. So here you realize something, right? What you realize is that you have y is equal to log to the base e of x, right? So when you try to find the y dx, if you use the formula there, it says first differentiate the function inside the logarithm. So here it is x. When I differentiate x, I get what? 1. Next, let me put the function at the denominator and write ln of the base. Here the in the example the base was what b, but here the base is what e. Right. So I put e here. Right. And now one thing you have to know, ln of any constant, let's say k, is the same as log of what? K to the base e. So ln of e is the same as what? Log of e to the base e. And this is equal to what? 1. This is equal to 1. You get it? Log of e to the base is equal to 1. So it means that this one is equal to 1. Then you get the answer is what? 1 over x. And that's the 1 over x you see. I'll show you a table to show you all the various rules of differentiation so that you can use it for your preparation. Just familiarize yourself with the table, okay? So that the whole point of it is that you don't go through the first principles. Once you're not going to the first principles and you're familiarizing yourself, you'll be fine. Okay, so let me show you the table. And it's right here, so you can see all of them. Okay, probably I'll add it to your materials. Yeah, so keep, keep on uh, asking questions and stick to this. Continue review it. It would enlighten you on how to do your differentiation. We'll solve a lot of questions to be able to come up to speed. And continue to like, share, and subscribe. Thank you.